Good afternoon, everyone. All right, almost everybody here. Any questions over chain rule homework? Want me to go over any problems or clarify anything for you? Everybody feels good about it?
Could you maybe go over question number 37 or 38?
And also the 15, please.
15, 37, or 38. Ooh, 38's. Okay, let me look at 37 first. So we have y equals in brackets x squared plus 1 minus 3x, but that's raised to the 5th. But then all of that is being cubed. Okay, so we have to kind of see what's going on here. We have an inner function. You could look at this whole thing in yellow as like the inner function. And then the outer function would be the cubed. So when you take the derivative, you start with the outer function. So we're going to bring the 3 down. And then we have the inner function, but we don't touch it, right? We just leave the inner function alone. Using the power rule, we subtract 1 from the 3 and get a 2 here. Is that okay so far? Then times, now we have to take the derivative of what's in yellow. But I have an addition symbol between the two things, right? And when I take the derivative of two things that are being added, I can do them individually. So I'm going to put a parenthesis here because I'm going to have two different things here. So that multiplication has to be able to distribute through to both of the derivatives. The derivative of x squared, that's a clean derivative. That's just 2x. But then I have plus. Now when I take the derivative of the other part, this 1 minus 3x to the 5th, I need to take its derivative, right? And that again is another like miniature chain rule. There's an inner function, right? It's like there's my inner function, and then there's my outer function. So let's just work on the derivative of that over here. I'd bring the 5 out. I'd leave the inner function alone to the 4th power times, now I have to take derivative of the green. The green, I can do them individually. Derivative of 1 is 0. The derivative of negative 3x is what?
Negative 3.
Negative 3, right? And I could maybe bring that negative 3 up here and make this negative 15 times 1 minus 3x to the 4th. That's the derivative of, don't have enough colors here. That is the derivative of this piece right here. I did that there. And so that's going to be going right here next to that plus symbol, negative 15, 1 minus 3x to the 4th. But remember, I have to close off the parentheses, this parentheses here. So that's it. That's without any algebra cleaning up or anything. That's just the raw derivative. Is that enough, or was there something else I needed to clarify? Make sense? I'm going to hold off on 38 because that's pretty involved. Number 15, I was asked about. Let's see, 15, y equals x secant of kx. Now, when you see a letter like K or A or B or something like that appear within one of these problems, you want to treat that like a constant. So this may as well be like the number 5, let's say. Okay, it's just some number, we don't know what it is. We're going to treat it like a constant, though, not a variable. So when I go to take the derivative of this, I have to first realize that there's a product rule right here. It's x times secant of kx. So I'm going to apply the product rule. So I'm going to take the derivative of this one first, which is 1, times the second function, secant kx, plus, now I need to take the derivative of secant of kx. We did one like this in class last time, and you have to be careful because of the kx. This is chain rule. We basically have an inner function, and then the outer function is this. So what is the derivative of secant of anything?
Secant tangent.
Secant tangent. So I'm going to have secant of something, tangent of something, but what goes in the secant and what goes into the tangent?
Kx.
Kx. You don't touch it, right? It's kx. So we've taken the derivative of the outer piece. Now we need to say chain rule, so multiply that times the derivative of the inside piece. So what's the derivative of kx?
K.
Just k.
Okay.
Because if it was 5x, your answer would be 5, right? If it was 10x, your answer would be 10. So if it's kx, the derivative is k. And then I have to finish off the product rule. Remember, it's derivative of the first times the second plus derivative of the second. This is the derivative of the second. I've finished there, times the first. So I guess you could write this secant kx plus kx secant kx tangent kx. All I did there was just brought the kx out front. Does that help? Okay, you might have some more questions. Let me talk about what we're doing today. So today we're going to try and cover implicit differentiation. We probably won't finish it. I don't know, maybe we'll see. So next time, which is on Tuesday, we'll either have more implicit differentiation or we'll finish it, and then we may start with the related rates section, which is word problems. And remember that exam 2 is a week from today. And I am going to send y'all a review for this exam for you to help you kind of prepare, because it's a lot of material. So I just want to kind of give you kind of like a template of what to expect. And look for that review to go out in the next like 48 hours. That way you can at least look over it on the week for the weekend. The test will cover up through implicit differentiation. I'll say it this way, it'll cover up through implicit differentiation only what we do today. So anything we do on Tuesday will not be on the test on Thursday. Okay. All right. So I thought I would start with a quiz. It's not, I'm not trying to, freak you out. Oh my gosh, we have a quiz. I just want to make sure you understand chain rule. So this is the way I'm going to treat this quiz. There's 2 questions. If you get one of them right, then you get 100. If you get both of them right, you get 110. All right. I'll launch a poll. The bad thing is I'm not going to give you like a whole lot of time on this. So there we go. The poll's been launched. Let's see what you can do in like 8 minutes. We're 5 minutes in. We'll go another 3 minutes. We have 15 students that look like they're done. I'm just going to go 1 more minute because 19 of you are done. Okay, 15 seconds. All right, closing the quiz in 5, 4. Oh, that's everyone. Okay. So sharing the results, that looks good. C and C were the answers. That is correct. I tried to make this quiz where you can kind of see that someone could come up with the other answers, but there's something wrong with them, right? Like look for number 1, this particular answer, whoever did this is doing the chain rule, right? They're saying, oh, the derivative of the square root of something is 1/2 times the square root. But then instead of putting the original inside function in here, they took the derivative of the inside function and put it in here. That's not correct, right? This one, they did the first part of the chain rule. They did the derivative of the outer function, but they forgot to multiply by the derivative of the inside. The last one is almost right, except there's no parentheses here. And you have to have the parentheses because this multiplication without parentheses means that you're only multiplying these two together, when in fact it's this distributing to both. So the parentheses have to be there. Okay, on the other one, let's see, the correct answer is C, right? So you have, again, an inner function and then an outer function. So you first start with the outside, 5, and then you're going to raise it to the 4th. But see, this student, what they did again is they didn't put the inside function in here. They put the derivative of the inside function. So they did the quotient rule on this, but that's too much too soon. You have to do original function in here, original inside, then times the derivative of the inside. This student, what did this student do? This student did the first part right, but when they came to take the derivative of this, they didn't do the quotient rule, right? They did derivative of top and bottom separately. Can't do that. And then on the last one, they kind of tried to do way too much all at one time, right? They brought the 5 out to the 4th, but then they took the derivative of this and they did it wrong. They did, again, no quotient rule. So correct answer is this. Any questions on that? C and C, we're good? Sure. Okay. I want to go back and I want to bring up something from 2.2. All right, this is section 2, chapter 2, section 2. This was the 4th note that we covered when I was talking about when you're talking about y is a function of x, and we want to say, hey, I want you to take the derivative, that there were all these different notations, right? F prime of x is one way you could say, hey, I need the derivative. You could just write y prime. the ones that I really want to pay attention to today are this notation, dy dx, and this notation right here. And I want to really make sure you understand what they mean. This first one means, another way you could write this would be d over dx of y, right? In other words, that y can just slide on top up here, and that's how it becomes the dy over dx. But when you read this d dx y like this, when you read that, what you're really saying is, I want to, how do I want to say this? We want to know the rate y changes if we change x by a small amount. Let me illustrate what I'm trying to say here. If I draw a picture, okay, remember this is the x-axis, we could say this is y. Let's say that we have some function here that does this. Okay, let's say we do that. And let's say I pick some value here, x. And I go up to the function here. What we mean by this, okay, what we mean by this in this picture is this. If we were to zoom in, okay, let's zoom in on that little section right there. If we zoom in, it's going to look like this. We're going to have our green point. We're going to have our blue curve coming off the side like that, right? I'm just zooming in on that little piece right there. What we're saying is, if I were to change x by a small amount, so let's say I move over, and I move my x over to let's say here, okay? On this picture over here, it'd be like, I'm just changing x just a little bit to some other point on the graph. That would be this point here. We're trying to find the rate at which the y changes. We call this dy. It's the change in y. And this right here is the change in x. And so if you take rise over run, think back to college algebra, right? Slope of a line. What we're trying to do is find like an approximate slope of the line right here. So we do dy over dx, right? So dy dx is the slope of a line connecting 2 points, but these 2 points are like infinitesimally close to one another, right? It's not like they're really, really far apart. We actually use the limit to bring these 2 points almost on top of one another, all right? So that's what dy dx is representing. It's the change in the y over the change in the x. Now, the reason that's important for you to understand that is because what happens if I write this? D dx of x itself. Well, that would just slide that x on top. That's just dx over dx, right? Well, what that means is if I have a specific, see this right here, this is a function. If we graph the function x, you all have to agree with me that the function x is the perfect diagonal line, but it's a line. Do you all agree with that from college algebra? Y equals x is just the diagonal. If I pick some point x here, right, go up to the graph, and then let's zoom in on that. Okay, so we've got our point. The function is coming out at a perfect 45-degree angle. That's not really 45, like a perfect 45-degree angle. And so if I pick another point right next to it, right, pick another point. So just slide over to the right a little bit, pick a point, plug it in. This is dx, but what would dy be? Because it's a perfect 45-degree, wouldn't dx and dy be exactly the same thing? Because it's a perfect diagonal. So this would also be dx. So what is dx over dx? What's that ratio?
1.
1. And that is why the derivative of x is 1. Does that make sense? The derivative of x is 1 because you're saying, basically the question is, how much does x change by if I change x by this much? But see, it's the same function, right? It's how much does x go up by if I change x by this much? So if I change x by 2, then it goes up by 2. If I change x by 3, it goes up by 3. So that ratio is always constantly 1. That's why the derivative of x is 1. I mean, does that make sense? We're here, this was a curve, right? This blue function was a curve, so it's not a perfect diagonal 45-degree line. So the rise over run is not always going to be 1, but it's because this is not, you know, a 45-degree line, right? That's why this is not 1. dy dx is whatever, you know, it depends on the actual function. You have to give me the function for me to be able to answer. Okay, so these notations, what's nice about these notations, as you're about to see, the biggest thing about this notation is that this dx on the bottom is telling you what's changing on the bottom. In other words, this is what we call the variable. Oh, that's too big. The variable, let me put it this way, x is the variable we are differentiating with respect to. That's kind of a new terminology for us. Because there's a dx on the bottom, that tells me that x is the thing I'm changing on the bottom, and then I'm trying to figure out what the change vertically is, right? And then create that ratio of rise over run, okay? Now you're probably sitting here going, what the hell are you talking about? Okay, so let me try and get us to where we're headed here, okay? I needed this before I could start this next part. If you're still unclear as to where I'm going with this, just hang tight. Okay, so we are now starting 2.6, implicit differentiation. All right, so far, everything that we have studied so far in this class has been y is equal to a function of x. In other words, we have, you know, y equals sine of x, or y equals x squared plus 1, or some, you know, like the quiz we just took, right? These were functions of x. We could say that, you know, y is this, or we could say y is this, and these are the functions, right? That's what we've been doing the whole time. We've been doing differentiating functions of x. So when we have this, okay, when we can isolate the y on one side of the equation, and then we can get the x's on the other side of the equation, we refer to that as an explicit equation. Okay, it just means that you can solve for one of the variables in terms of the other. You can get y by itself with x's on the other side, or you can get x's by themselves with y's on the other side. Either way, if you can do that, that's called an explicit equation. I like to think about it this way. If you look at both of these functions, if I tell you what x is, right? If I tell you what x is, can you tell me what y is? Right? If I tell you, hey, plug in x is 2, could you tell me what y is? Sure. If I tell you, hey, plug in x is 5 here, could you tell me what y is? Sure. That's an explicit function. I give you one variable, and it's very simple for you then to determine the other variable. That's explicit. This section is called implicit differentiation, not explicit differentiation, implicit. So there's something different between explicit and implicit. We need to understand the difference. Some equations are very difficult to write in explicit form. When we actually try to like solve for y or solve for x, we run into algebra problems. So here's some examples. These three are examples of explicit equations. This is solved for y, right? X is over on this side. If I give you an x, very simple, you give me what y is. This one, oh, that square root is supposed to go all the way across. I don't know why it's not doing that. Don't worry about it. It's square root. Okay, so if I give you x, you can give me y. Look at this one. If I give you y, you can give me x, right? But on this one, on this last one, if I give you x, is it easy for you to then tell me what y is? Like if I told you x is 10, could you tell me easily what y is? No, not easily, right? If x is 10, y equals 2 would work, wouldn't it? But that's just because I visually inspected it. It's not that easy. If I give you y equals 12, you're not gonna be able to figure it out easy. So this equation is still explicit, okay? This last equation is still explicit, but we would say there that x is a function of y. You can determine x if someone hands you y. The other two are referred to as functions of x, because if you give me x, I can give you y easily. Does that make sense? I'm going to write that down. These two are both y's are functions of x. This one, you would write x is some function of y. It's different. But either way, those are called explicit equations. Implicit, these are some examples. So notice on here, look at this one here. I'm going to actually copy these. Let's take these to our notes. Let's talk about why these are implicit and not explicit. So look at the first one, x squared plus y squared equals 16. Does anybody recognize that equation from pre-cal or college algebra? Anyone know what that equation is, what it draws, what the graph of that looks like?
A circle.
A circle, good. With what radius? Do you remember? This is the generic equation of a circle, x squared plus y squared equals r squared. So this would be a circle of radius 4. Okay. Now that's not critically important, even though I'd want all of you to know that that's the equation of a circle. It's okay if you don't. Now you do. It's not simple. If I give you x, it's not simple for you to tell me what y is. And if I give you y, it's not simple for you to tell me what x is. Well, you might say, okay, well, great, I'll just solve this for y. So let's solve for y. I'm going to subtract x squared on both sides. Is that okay? That's just algebra, just subtracted x squared. Okay, I almost have y by itself. To get y by itself, I need to take the square root on both sides. But because you're taking the square root, you have to do plus or minus. Anytime you take the square root on both sides of an equation, you must do plus or minus. So now look, this is a problem, because now if I hand you x, right? What if I give you x is 0? Okay. What if I tell you to plug in x is 0? Can you tell me what y is?
Plus minus
Maybe
4.
2 answers, no.
It's 2 answers, right? It's either positive or negative 4. So it's actually 2 different things. So yes, you can kind of tell me, but you can only tell me that it's one of 2 things. You can't tell me exactly what it is. That's a problem. That's a problem. And I'm going to show this to you visually. Let me bring up Desmos. I'm going to have Desmos graph this for us. X squared plus y squared equals 16. So there's my circle of radius 4. So think about what we've been doing in this class. We've been finding the slopes of tangent lines, right? So right now, let's say I give you a value of x. Let's say I give you that x is 2, okay? Do you all see that there's actually 2 points that correspond to that x value? There's 2 points. So if I ask you for the slope of the tangent line at x equals 2, there's actually 2 different answers. There's this one, right? There's that slope, and then there's this slope. So which one am I talking about, right? It's almost like me giving you x equals 2 isn't enough. You need more information to be able to determine which of those 2 it is. Do y'all see how that's inherently a problem? The thing that's causing the biggest issue is that a circle is not a function. Why is a circle not a function?
Because
I see people
X
doing
has
this.
more than two value,
Vertical
one
line
than one
test.
value.
Yeah, fails the vertical line test, right? Fails the vertical line test. Everything we've been doing so far, we've been dealing with functions. And so if you're dealing with a function, right? If I give you a function and I give you a specific X value, there is only one tangent line possible because there's only one point on that function that corresponds to that X value. But with a circle, there's more than one, right? So like I said, we need a way of nailing down which one we're talking about. Okay, let's look at the next one. Holy crap. You feel like solving that for Y? It's not happening, okay? It's not happening. Same with this one. This equation right here, there's no algebra that you have learned. There's no algebra that I have learned. There's no way you can solve either one of those equations for Y, okay? You can't. It's actually algebraically not possible. And so, you know, what do we do? Because I'm going to type this one into Desmos right now, x cubed plus cosine y equals x plus y squared. Interesting. That equation is a relation, it creates a relationship, and we can plot all the solutions to this. Remember, every point on this, it's not giving me points. Huh, interesting. Doesn't like to give me points. That's all right. Every point on this, right? Whatever that point is, whatever that X is, whatever that Y is, if we take that X and plug it in here, we take that Y and plug it in here, we should get a true equation. It should be true. The left side should equal the right side. So every point on that blue curve is a solution to that equation. So we have solutions to it, right? This is what they look like, but this is not a function. But do you still see we can talk about tangent lines? Like I could say, I think it's completely reasonable for me to ask you for the tangent line here. It's perfectly reasonable for me to want to ask you about the tangent line here. But again, we're going to run into that same problem. This point here corresponds to some X value, but wait a minute, so does that one. So I actually have two tangent lines there, right? Same with this one. This X corresponds to another Y value, and there's a different tangent line there, right? So with these implicit equations, we have this idea that we no longer have functions, traditional functions with a vertical line test. So we can pick an X value, but have multiple outputs. And so it's really tough to talk about tangent lines. Is this making sense? I'm going to show you the last one because the last one's really cool. Cosine xy equals 1 minus sine y. Cosine of x times y equals 1 minus sine y. Whoa. Okay, I'm pretty sure you weren't expecting that, right? What the? Okay, Desmos is having a little bit of trouble graphing this right now. Let me zoom in a little bit more. Let me get, yeah, okay, so Desmos did okay there. So check this out. Again, this illustrates the idea of, look, if I give you an X value, let's say X is 2, look at all the possible tangent lines. You have a point here that looks flat. That one there looks like that. This one here looks like that. Keep going up. Looks like we have one here. We have another one there. Maybe another one here, another one there. Do y'all see all these different tangent lines that could be possible here? So we have two challenges. First of all, first challenge is, how do you even take the derivative of an implicit equation? How do you even take the derivative? Because we're not solved for y, right? You've got y's and x's mixed together. How do we differentiate something like that? That's the first challenge. The second challenge is if we can do that, if we can somehow make sense that there is a derivative to this, how do we find the tangent line that we want? How do we find, the right one out of all of these? So it's kind of two tasks we have to, or two challenges we have to overcome here. Okay, and that's what we're about to do. So this is just me explaining more. Okay, so blah, 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 blah. Okay, so in order to do this, in order to figure out how to do all this, we now study a new form of differentiation called implicit differentiation. All right. So that's what today is about. What is this thing called implicit differentiation? Here we go. Buckle up. We're going to start with that first example. If y squared equals x squared, I'm sorry, if, what the hell did I just say? If x squared plus y squared equals 16, I want us to find dy dx. In other words, remember, that's just the notation for the derivative, right? That's the notation for the derivative. Where is it? That we said before, right? If y is a function of x, dy dx means just give me the derivative, right? Give me the slope of the tangent line. Problem though, this is not a function of x, right? So how do we do this? You ready? This is the way it's done. What you're going to do is you're going to just write the equation down. And you're going to do something to both sides of the equation, all right? We've been doing this our whole lives with algebra, right? Multiply both sides by a number, add or subtract by a number, right? Both sides. We're going to do something on both sides. But what we're going to do is not really something you would expect. We're going to take the derivative on both sides of the equation. Watch the way I do it. I'm going to write, okay, I want to take the derivative with respect to x. And I want to do that on the left side of the equation. And then I want to take the derivative with respect to x on the right side of the equation. Okay, so this is just me symbolically telling you that I'm about to take the derivative on both sides. Now, on the left side, I have addition between two things, right? So the rule in addition is that I can take the derivative of each one separately. I'm not going to do it yet. I'm just going to write it down what I'm about to do. I'm about to take the derivative with respect to x of x squared. Then I'm going to add to that the derivative with respect to x of y squared. And then on the other side, I'm going to take the derivative with respect to x of 16. All right. Here's where things get weird, right? Does this all make sense so far? This is just like a notation, letting you know I'm about to take derivatives. I split it up because I had an addition. So everything up to this point's okay? All right. On this first one, I want you to pay close attention to the fact that the variable in here matches the variable in here, right? These two variables match. When these two variables match, you're going to do the derivative exactly the way you've been doing the derivative. What is the derivative of x squared if x is the variable that we're talking about here? What do you think it should be?
2x.
2x, right? 2x. Okay, so that should just be 2x. Nothing new, no difference, right? Everything's still the same. Okay, so we're happy here. I'll put a little happy face because nothing is different there, right? This is where things get crazy. When we do this derivative, notice that the variables do not match, right? They don't match. And because of this, we cannot do the derivative the way we just did it. The answer to this is not just 2y. And so what we have to do is treat it as a chain rule. So what do I mean? Over here, I want you to think of how you would take the derivative of y squared. I want you to think of y as being the inner function and the 2 as being the outer function. Okay? Do the chain rule. First thing you deal with is the outside, right? Okay, so if you take the derivative of the outside, you're going to have to bring a 2 out front, yes? And then y to what power? I'm sorry, I shouldn't have said y, but it is y. It would be y to the first power, wouldn't it? Because you're supposed to leave the inside alone, don't touch it, and then go first power. That makes sense? That's just the derivative of the outer function. Now you have to take the derivative of the inside function. What is the derivative with respect to x of y? It's not 1, right? That's not 1 anymore, because it's only 1 if it's dx dx, right? It's dx dx, it's 1, but if it's dy dx, well, I don't know what that is. I'm going to take that 1 off that y. Is that okay, everyone? I'm going to continue the chain rule. I'm supposed to multiply by the derivative of y, right, with respect to x, which I don't know what it is. Y'all understand? I do not know what that is. Dy dx is something I don't know, but I'm actually very happy to see it. Why am I happy to see it? Because that's what we're trying to solve for. We are trying to figure out what dy dx is, and it just appeared within this new equation that we're creating. So here, because the variables matched, it was just a traditional derivative, nothing special, 2x. Here, because the variables don't match, I have to apply the chain rule. So 2y to the first power first times the derivative of y with respect to x. The derivative of y with respect to x is dy dx. We are done with the derivative of this. Now's a good time to ask a question. If you're a little lost, we will do more examples and hopefully it'll start to become a little more clear. I bring the equal sign down. Okay, now on the right side, we're taking the derivative of 16. And 16 is a constant, and I have good news. No matter what, the derivative of constant is always 0. No matter what you're differentiating with respect to. If you're differentiating with respect to x, the answer is 0. If you're differentiating with respect to any other variable, the answer is 0. So this is 0. You with me? So I started out with this equation. I wanted to know dy dx. I did implicit differentiation. This right here is the implicit differentiation step. You're taking the derivative on both sides with respect to x. Split it up. The first one's just a traditional derivative. The second one, not so good, but I just have to apply the chain rule. And that's why I get 2y dy dx and then derivative constant 0. I am now going to isolate dy dx because that's what I was trying to solve for. I'm going to isolate it, meaning I'm just algebraically going to move things around. So I think it's natural to just move the 2x to the other side, make it negative 2x, right? Subtract 2x on both sides. And then divide both sides by 2y. And then I can cancel the 2's. So I get negative x over y. That is the derivative of that. Now, what does this all mean? What is all? I'll bring that back up. Hold on. Let me go back up. Let me bring this circle. I'm going to copy this. I'm going to bring this into our notes here. This was the equation, right? This was, yeah, the graph of that equation. That was it right there. So what does this answer really mean? What this answer means is that if you want to find the slope of the tangent line, right? If you want to find that slope, if you want to know what it is, you're going to have to supply me with what? An x and a y. Give me the x value and give me the y value you're talking about, and then I will tell you the answer. So how about we pick a nice point here? How about we pick a point that we can all agree, if we just go out 45 degrees, do you all agree that whatever this point is, The X and Y coordinates are exactly the same? Because I went out 45 degrees? So if this X and this Y were the same, what would this answer give me? If both the X and the Y were the exact same number, what answer would I get for the derivative?
1
With the negative though, right? See
with
that
the negative. Yeah.
Yeah, so it'd be -1, wouldn't it? And does that look like that's the slope of the tangent line there? It does, doesn't it? What about this point right here? What are the actual coordinates of that point? What's the X coordinate? What's the Y coordinate?
0, 4.
0, 4. Okay, so tell me what this equation would give you if you plugged in 0 for X and 4 for Y. What would your answer be?
0.
0. And is that the slope of the tangent line there?
Yes.
Yes. What if you did the point here on the bottom? That's 0, -4, right? If you plugged in 0 for X and 4 for -4 for Y, wouldn't you still get 0?
Yes.
Yeah, so you would get the slope of the tangent line. Here's a cool one. What about this point? What's that point right there? What's the X and Y coordinate? X is what? 4, Y, the Y is 0, right? What would happen if you try and plug in 4 for X here and 0 for Y?
Undefined.
Undefined. But wait a minute, don't vertical lines have undefined slopes?
Yes.
I mean, it's behaving exactly the way it should behave, right? This is the formula for the slope of the tangent line anywhere on that circle. All you have to do is be able to provide me the exact point you want me to talk about, and then I will provide you the slope of the tangent line. But it requires both the X and the Y coordinate. Let me try one more to see if you really understand this. What if I pick this point right over here? I go out. So this is like, 45 degrees, but the other way, this point right here. What can you tell me about the X and Y coordinates here? Are they the same?
Yes.
Yes.
Kind of, right? Like whatever the X is, do you agree this is a negative number?
Yes.
And do you agree then I have to go up, so that would be a positive number?
Correct.
But they're the same value, right? So like if this is -2, like if this is -3, then that's +3, right? What would happen if I plug that into this? What would I get?
1.
1, right? And that matches with the slope of the tangent line here. Okay, we need to do more examples, okay? But I hope you're starting to see that this is a very nice way of finding the slopes of tangent lines for any curve. It no longer has to be a function of X. It no longer has to pass the vertical line test. And that's pretty powerful, because when you think about things in the real world, right? When you think, let's say that you're tracking something on the ground that's moving, right? And you want to know at a specific point the slope of the tangent line. That slope of tangent line, like in a physics class, that slope of tangent line could actually represent something like the velocity of that object at that point in time. You don't want to be restricted or confined by the idea of whatever is drawn has to pass a vertical line test, because in the real world things move around, and they do things that maybe you're not predicting they're going to do, and we still want to be able to find slopes of tangent lines and not be crippled by the idea that it's not a function anymore. So implicit differentiation allows you to still do calculus on things that aren't functions. So it's very, very useful. Okay, before I go on to the next example, I just want to be really clear with everyone the way this is working. So this is kind of like let's do these really quick problems. What is the derivative with respect to X of X cubed?
(3x squared).
3x squared. No, nothing surprising, right? Nothing new. The variable on the bottom is the variable in here. The derivative is what we've been doing. Now, what is the derivative with respect to X of Y cubed?
would it be 3y times dy
3y
over,
squared,
yeah,
3y
3y
squared
squared times dy with respect to dx?
Yes, you can just say dy dx, that's fine.
Okay.
You can say dy over dx.
Okay,
That's your chain rule, okay? So what's happening here is we're saying, oh, we've got y and x don't match anymore. So I'm gonna treat this like a chain rule. Power rule first, 3 comes out, raise the power to the second, leave it alone, right? Leave it alone, leave the inner function alone. Then multiply times the derivative of y. The derivative of y with respect to x is dy dx. Y to the 5th. 5, y to the 4th times dy dx. Understand? Because the variables don't match, it's like you're going to do the derivative the way you want to do it, but you always are going to have this dy dx slapped onto the outside. That's always going to come out in the chain rule, always. When these variables don't match, you're always going to have that dy dx pop out. Let me give you another one. What about the derivative with respect to x of sine of y? That's still chain rule because x and y don't match, right? So what do y'all think?
Cosine x, cosine y,
Cosine y first times
dy dx.
dy dx. Okay. Contrast that with this derivative with respect to x of cosine, of sine of x, right? And that answer would just be cosine x. I wonder if anyone's caught on to the fact that what we're doing over here is exactly the same as what we're doing here. Look at this one. What if I told you to do chain rule on this one? You would bring the 3 out first, x squared, right? Then what would you multiply by? The derivative of x,
X.
right? With respect to,
x, so it'd
Which
just be
would be-
dx,
which is
1.
1. Do you see we actually have been doing this the whole time, but we actually didn't know we were doing it? Like there's always chain rule, but when these variables match, you're always going to get a dx to come out, which will always be a 1, which means we don't even need to consider it. But if the variables don't match, you're not going to get a dx, you're going to get a dy dx, and dy dx is not 1. That's what I was trying to illustrate when I drew these pictures earlier. Where are they? I don't know where they are. Where the hell are they? I don't know where they went. Oh, here, where I was saying, look, you know, dy dx is the ratio of this to this, but if you're doing dx, that's the perfect diagonal, then that ratio is always 1. Trying to get you to see that. Here, how about this one? What is dy of x to the 5th?
Would it be 5x to the 4th times dx over dy?
Exactly. See, in that case, again, these variables don't match, right? So the first thing you do is you use the power rule on x to the 5th, which is 5x to the 4th. But then you have to take derivative of the x with respect to y, which is dx dy, not dy dx, dx dy, which is still not 1 because, right, these variables don't match. Does that make sense? Give you another one. What's dt of x squared?
2x times dx dt.
Exactly, dx dt. Who has questions? Let's do more. You ready? I'm gonna throw a curveball. Here comes a curveball. What's d dx of x squared y cubed? Ooh. Okay. Crap. We have to take derivative of this, right? We take derivative of this. Well, wait a minute. I'm taking derivative. I've got x squared what y squared? X squared what y squared? X squared
Multiplied. It's a product.
multiplied, right? This is a product. Well, guess what? That means you have to use the product rule. That means that when you take this derivative, you're going to have to take the derivative with respect to x of the first one times the second one plus the derivative with respect to x of the second one times the first one. Do y'all see that product rule? We have the derivative of a product. The derivative of a product is the derivative of the first one times the second one plus the derivative of the second one times the first one. Which would be, let's see, what's this one?
2x.
2x times y cubed plus, let me call on somebody. How about Shams? Shams, you there? I saw Shams and then Shams disappeared. Landon? Oh, wait, Landon, I called on your last name. Chloe?
Yeah.
Are you following, Chloe?
Yeah.
Okay,
think
what
it
about
should
can you finish
be-
this off?
3y squared times dy over dx times x squared.
3y squared times dy over dx times x squared. Perfect. That's what the derivative of this is. Okay. So I think this illustrates how important this notation is. This ddx or ddt or ddy, it tells you the variable you're differentiating with respect to, right? It's very important. And that's why that notation is preferred when you're doing implicit differentiation. If you're just using the other notation, it doesn't make clear what the variable is. So I'll share a quick story with you. And you know what? I'll pause my recording because I don't think I could
I
handle
was
that.
expecting that. I was
Yeah.
like, it will turn out that it's your wife or something.
I dated a girl that I was in grad school with. It didn't work out too good. Two math brains in the same room don't always work out well. Okay, let's get back to business. All right, this was all just kind of just to make sure you understand dy dx and you know what the variable is. Let's go back to those functions again that we started class with, and let's see if we can't find dy dx for something like this one. What's really funny is back in those days, every night the DJ would have they would play different music every night, you know, and when you left the club for like $5, you could get a CD of what they played that night, you know, like the whole night worth of music on a CD. I still have the CD from that night, from the music that played that night. It's pretty cool actually when you think about it. Okay, here we go. Here's the equation. I want us to find dy dx.
So you're recording now? Or
Yes, I did hit.
oh,
let me
thank you.
double
Thank you.
check.
Sorry.
Thank you for double checking because I could have forgotten that easily. Yeah, I'm recording. So I want to find dy dx. So as soon as you see that, see this dx right there? That is telling you what we're differentiating with respect to. So anytime we take derivative of something with x's in it, we're going to do it like we normally did. Anything that has y's, we're going to have to apply chain rule. Make sense? So I'm going to start off. Here's the implicit differentiation step. I'm going to take derivative with respect to x on the left. And then the derivative with respect to x on the right. I need to email her. I mean, I haven't talked to her in a while. It's been probably about 10 years. Okay,
I cannot imagine what she's doing right now because she was programming robots at that time. So
I
now,
don't know. Yeah, I don't know. She could have changed jobs. She was married. She was married and I think had some kids. So I'm not sure. Okay, here we go. So on the left side, we have addition, right? We have addition. So we can split this up into two. ddx of x cubed. That's going to be just a regular old derivative. ddx of cosine y. Well, that's going to not be a regular derivative because y and x don't match there. So we're going to have to do some chain rule. On the right side, split it up as well because there's addition. So derivative with respect to x of x, and then the derivative with respect to x of y squared. So the first one over here is going to be our traditional derivative, and then derivative over here is going to be some chain rule. So why not give you a second, see if you can write out the next line. I'll give you 34 seconds. So I put the answer up there. Did you get that? Everyone understand that? Regular old derivative. 3x, derivative of x cubed is 3x squared. Derivative cosine of y with respect to x, we first take derivative cosine of y, which is negative sine of y. And then we have to take derivative of y with respect to x, which is dy dx. And then derivative of x with respect to x is 1, right? That's what I was expecting her to say that night, right? 1, but, and then this one, 2y, and then the derivative of y with respect to x, which is dy dx. Okay, we're not done because it said find dy dx, right? So this is where things are going to become complicated because you have to isolate dy dx now. We actually need to get the dy dx by itself on one side of the equation. So it's just algebra now, but it can be a little bit messy. So here's the kind of rule of thumb. To solve for dy dx, what you do is you take everything that has dy dx in it and move it to one side of the equation. Everything that does not have a dy dx in it and move it to the other side of the equation. So here's what let me write the next line, and you tell me if you can follow what I did. You know, see what I did there? Leonard, you there?
Yes, I'm here.
Okay, do you follow what I did?
Yes, you just move everything. Well, yeah.
Yeah,
You subtracted 1 and then move everything else to the right.
yeah. So I subtracted 1, which made it a negative 1 on the left. And then this was a negative sign, y dy dx. So I added it to both sides, and that's why it's over here now, right?
we can never put that divide into the other side because it's already attached to the dy dx, right?
You can never do what?
Like we can never move, for example, 2y and
Oh,
sine
yeah, no.
y to the other side.
That's
It's
right, because
like
it's
trapped.
attached through multiplication.
Uh-huh.
You can
Okay.
only move terms around if they're added or subtracted. Now, why do you think I did this? Why do you think I got all my dy dx's on one side and everything that didn't have dy dx on the other side? Why do you think I did that?
You can factor out the dy dx.
I can
Or take
factor
it
it
out.
out. Exactly. Since they both have a dy dx, I can factor dy dx out, which leaves me with 2y plus sine y, right? And then I can just divide both sides by 2y plus sine y. And by doing that, I'll get my final answer. 3x squared minus 1 over 2y plus sine y equals dy dx. Remember, this will give you the slope of the tangent line at where though?
dy dx, or given a point.
Given a
X and
point,
Y.
right? So at xy. You know, everything we've been doing up to this point has been, okay, this will give you the slope of the tangent line at x, and all you needed to give me was x. But again, because this is an implicit equation, in order to find the slope of the tangent line, look at the answer. It has x's and y's in it, right? So in order for me to give you what the derivative is, you're going to have to provide me both the x and the y coordinate of the point you're talking about. So let me give you one to work, okay? Let me give you one to work. I want you to find the equation of the tangent line to the curve. Let's see. X squared plus 2xy minus y squared plus x equals 2 at the point 1, 2. Okay, write it down. Don't get started yet. I want to talk to you about it before you do anything else, okay? I want you to find the equation of the tangent line, right? That means you have to go and use that thing we've been using this whole class so far. This good old point slope formula for a line, right? You're going to need that. You know the point, don't you? You know x1, y1? Yeah, it's right here. All you need to figure out is what the slope is, which means you need the derivative, right? You need the derivative of this thing at this point. Do you understand what you need to do? Go back to the previous problem. You see this right here? Do you remember when we took the derivative, we were done taking the derivative right here. And then the rest of it from here to here was algebra, wasn't it? Was algebra. And that's how, what we did is we worked the algebra down until we got dy dx by itself. Okay, right? If you're trying to find dy dx and you are given the point, here we're given the point, aren't we? 1, 2. You do not have to do the algebra. You could just plug the 1, 2 in here. You could do x and y. You could replace all your x's with 1s, all your y's with 2, and then go solve for dy dx. It's much cleaner, easier algebra if you do it that way. You don't have to. I recommend it though. So in summary, what you're going to do here is you're going to do implicit differentiation with respect to x on both sides. Once you're done with the derivative, you're going to replace x with 1, y with 2, solve for dy dx. That will give you the slope of the tangent line. Plug it in there and you'll have the equation. Go for it. I'll give you a few minutes. Why don't you let me know when you're done? We won't go too long, but let's just see how y'all do with this. I'm gonna start working it myself here. There's still quite a few of you working on this, but we only have about 14 minutes left. So I want to make sure that we understand at least the derivative of this. So on this derivative, I didn't show a lot of my work here. I just did it in my head. But when I'm taking derivative on the left side, I have, 1, 2, 3, 4 terms. So I can just do these individually. Derivative of x squared with respect to x is just 2x, your traditional derivative. But 2x times y, I have to treat like a product. So what I did is I said, okay, the first function is this one, here's the second function. And then I applied the product rule. The derivative of 2x is 2, that's this 2. So that's the derivative of the first function times the second, plus product rule, the derivative of the second function. Well, the derivative of y with respect to x is dy dx, and then times the first function, 2x. So everything with the gray arrows is me doing the product rule on this in green, or yeah, that's everything here. And then I had to continue minus, now derivative of y squared. Okay, well, y, I'm differentiating with respect to x, so I'm going to do 2y first, and then the derivative of y with respect to x. Then plus, now derivative of x, well, with respect to x is just 1. And on the right side, derivative of the constant is 0. Are there any questions on that? That all makes sense? At this point, I did not go solve for dy dx. I just said, okay, I'm trying to find dy dx at this point. So I replaced all my x's with ones. This x got replaced with ones. And then all my y's got replaced with twos. And once I did that, I got to this line, then I just cleaned things up. I just put all my numbers together, 2 + 4 + 1, give me 7. And then I had 2 of these dy dx's and I'm subtracting 4 of them. That leaves me -2 of them. And then the rest was just algebra. Just move the 7 over, divide by -2, and I get a +7/2. Make sense? I'd say there's, a little bit, there's a lot of places you can go wrong here, right? I mean, you have to be real careful. Let's check this. The original function was, let's see, x squared, x squared plus 2xy minus y squared plus x equals 2. So there's the graph of the actual curve. This is the implicit equation graph. We were looking at the point 1, 2, which is that black point. And the equation of our tangent line turned out to be y minus 2 equals 7/2 x minus 1. There it is. We got it. We got the equation of the line that is tangent to this curve at that point. All right. Let me see, 10 minutes. Let's do this. How about, I'm making one up here. How about if we have tangent of x over y squared, x over y squared equals equals x squared plus y plus xy. Find dy dx. This will be our last example. All right, this is an implicit equation. There's no way I'm solving this for y. So I've got to start taking the derivative. So the derivative on the left side with respect to x will be the derivative of tangent of this thing. And then equals, I'll have to take derivative with respect to x of x squared plus the derivative with respect to x of y plus the derivative with respect to x of x times y, right? That's what this means. Let's do the right side first. I think the right side's the easier of the two. Christian, are you there? Is this making any sense?
I think so.
Okay. Help me out on the right side. Go ahead and give me these derivatives. So what's this one?
2x.
2x, okay. 2x. And then what about this one?
dy dx.
dy dx. Okay, good. Okay, now Christian, on this one, what are you going to need to do?
Product rule.
Product rule, right? We're going to do a product. Do you want to keep going?
So it's 1.
Y, okay, so you did derivative of the first one, right? Derivative of x, I gave you 1, and then times y. I'm going to actually write the 1 times y.
Yeah.
Then plus, now what?
Dy dx
dy dx, that's a derivative of the second one times
X.
x. Perfect. Everyone understand that? What's in blue is the product rule on this. Derivative of the first one times the second plus the derivative of the second one times the first. When we took the derivative of x, we got 1, but when we took derivative of y, we got dy dx. Good, good. All right, Kevin, are you there? Yep.
Yeah, I'm here.
What do you think of the left side, Kevin?
The left side is, are you asking me to solve it or what?
Well,
I just,
just kind of, let's talk through it. You're going to first have to take, this is chain rule, right? You see the chain rule?
mm-hmm.
Okay, so you start with the outermost function, which is the tangent. So what's the derivative of tangent of something?
Secant squared x.
Secant squared x. So for us, we're going to put secant squared of what?
Secant squared of x over y squared.
X over y squared. So we're not going to touch the inside. Good. Then times, now, Kevin, this is the part that's going to suck, is we've got to take the derivative of the inside piece, right, in yellow?
Yeah.
But that's going to be quotient rule?
Yes.
Okay, do you want to do that?
Yeah, I'll solve it. I just
Okay.
need a little bit more time with it.
Yeah, that's fine. Everybody can work on that. Do a little quotient rule on this. Just be careful. Remember, derivative of x's, you know, that's normal, but when you take derivative of the y stuff, it's not normal. So it's going to look really weird. I'll start setting it up. One thing I know for sure is that the bottom is y to the fourth, because when you do the quotient rule, at the end of it, you get the bottom squared. So when you square y squared, you get y to the fourth. It's really the top part that's going to be the tricky part. Let's talk through it, Kevin. When you do quotient rule, you start with the derivative of the top, right? You're on mute still. We can hear you.
Sorry,
Yeah.
can you repeat that? I couldn't hear you clearly.
Yeah, no, so I said, I'm gonna help, let's walk through this together. When you're doing quotient rule on this, you start with the derivative of the top, right? So what would the derivative of the top be? We still can't hear you. Can you not hear me?
I'm sorry, like my computer's weird.
Okay.
I'm switching over to a tab to see quotient rule where I have some of my notes.
Okay, well, I'm
And-
gonna tell you the quotient rule. You just
Okay.
follow me. So the quotient rule says we first take the derivative of the top. So what's derivative of the top?
X.
What's a derivative
Wait,
of?
no, the derivative of the top is, it's 1.
1, okay. Then the quotient rule says times the bottom.
Yeah,
So
times y squared.
okay, and then the quotient rule says then you subtract. Now the important one, what's
It's
the derivative of y squared?
2y times dy over dx.
Good. And then to finish the quotient rule, you then multiply that times the top, which is
X.
x. Okay, and then it's all over the bottom squared, which is where I get the y to the fourth from.
Yes.
Everyone follow that? Ash?
I have a question.
Yes.
Why did you get 1 times y for the derivative of the top?
Okay,
Because
what
it
is the
shouldn't be y
derivative of,
squared.
did I say y? I'm not sure. You're
And
talking
that-
about right here?
Oh, yeah, sorry, I was looking at the blue. Never mind.
Okay.
Sorry.
No, it's okay. This is our derivative. Are there any other questions on this? I mean, we have not, we're supposed to now solve for dy dx. We're supposed to get dy dx by itself now. This is going to be a problem, but it can be done, all right? And I only have 2 minutes, so I'm going to have to move fast. So see if you can follow me through this algebra. The first thing I'm going to do is I'm going to take this big fraction right here. I'm going to split it into two fractions. So I'm going to put the y squared over y to the fourth. That's this 1y squared over y to the fourth. And then I'm going to subtract from that the 2y dy dx times x all over y to the fourth. And then equals the other side, 2x plus dy dx plus y plus dy dx times x. Okay, sorry, I forgot to highlight there's another dy dx here. We're trying to solve for dy dx. Okay, so what I did, the reason I put this into two fractions is that now what I can do is take this entire secant squared and distribute it through here, and that will allow me to free this dy dx up. I'm gonna run out, I'm gonna run out of time. Let's leave this one for now because I'm out of time. You're gonna have an opportunity in your homework to do this. I would say for homework right now, on implicit differentiation, let's keep it. Let's keep it simple, okay, for this. I'm right now for today, I just want you to look at those 4, 5, 7, 8, 10, 11, 12, 13. And then I did number 20 in class today. So what I'd like for you to do is instead of 20, I want you to do 19. All right. And then the others that I'm going to highlight in blue, just those were just not yet. Okay. Not yet. So for the problems here in yellow, you're supposed to find dy dx using implicit differentiation, and you're supposed to solve for dy dx. As you do your homework, you're going to see that really, once you understand the implicit differentiation, I think really the hard part is getting dy dx by itself, because the algebra is messy. It can be messy, but you practice and see how it goes, and then I will plan on having implicit on the test. Just I'll keep it kind of minimal in terms of what I ask. It won't be like some of these homework problems are going to be very complicated, as you'll see. All right. So I'll keep it pretty simple on the test, meaning it'll be, probably something like what we did here today. This one might be a little too complicated for the test, but this definitely is fair game, something like this. I think the differentiation here is pretty straightforward. This one's also pretty straightforward because, yeah, there's not a whole lot of chain rule or anything happening, product rule, quotient rule. See how the homework goes. Any questions? We have more to do in this section, okay, but we'll do that next week, and then we'll get into word problems. All right. Y'all have a good one. I'm gonna, let's see, it's 2:42. Oh, yeah, that's it for today.
Yeah, have a
I'll
good
be in
day.
office hours at 4.
Have a good weekend.
You as well.
Thank you. Bye.